At 6:51 in the evening, Eastern Time, on Friday the 24th of July, a 407-foot rocket lifted off from Starbase in Boca Chica, Texas, and about an hour later, most of it was at the bottom of two different oceans. That is not a criticism. That was the plan for the ship. It was not the plan for the booster. Starship Flight 13 has been reported almost everywhere as a success, and by the standards SpaceX set for it, that is broadly correct. It deployed 20 operational satellites, the first time any Starship has carried a real payload rather than a mass simulator. It survived reentry. It came down where it was supposed to. But the most important thing that flew on Flight 13 was not the rocket, and almost nobody has written about it. 6 of those 20 Starlink satellites had been modified before launch. Each one carried a suite of cameras. And after they separated, instead of simply drifting away and getting on with being satellites, they turned and looked back at the ship that had just released them, photographing its heat shield and transmitting those images down to operators on the ground. The final 2 used lights to illuminate the vehicle in orbital darkness. SpaceX spent part of its first operational payload on taking photographs of its own rocket's belly. In the next 30 minutes, I'll explain why that decision tells you more about the Mars timeline than anything else that happened on Friday, walk through exactly what Flight 13 did and did not achieve. Explain the word that appears in every technical description of this mission and almost none of the headlines, and lay out the arithmetic that determines whether anything reaches Mars in this decade. I'll also be direct about what this does not mean, because both the celebration and the mockery around this program are usually built on the same misunderstanding. Let me start with what actually happened, because the flight had a difficult run-up. Flight 13 used Booster 20 and Ship 40. It was the second flight of the version 3 configuration, following Flight 12 in May. Version 3 is a substantially different vehicle from the one most people picture. Raptor 3 engines, an integrated interstage rather than a separate structure, and 3 grid fins on the booster instead of 4. Before it could fly, the Federal Aviation Administration had to close out its review of the previous flight. A mishap investigation report from Flight 12 was completed, and on the 13th of July, the FAA concluded its review and cleared the path for subsequent launches. The first attempt came on the 16th of July, and it got to 0. At T-0, with the countdown complete, the vehicle's flight software triggered an automatic abort. 4 Raptor engines had failed to meet acceptable starting parameters, and the software shut the sequence down before the vehicle left the pad. I want to pause on that, because it is genuinely one of the more impressive things in this entire story, and it got covered as a delay. A Raptor engine start is a controlled explosion that has to happen inside a very narrow band of conditions. Turbopumps have to spin up correctly, chamber pressure has to build correctly, propellant flow has to stabilize. The engines are being asked to do this simultaneously, at the base of a fully fueled vehicle sitting on a launch pad worth an enormous amount of money and years of construction time. On the 16th, 4 engines out of the booster's set did not come up to specification. The software noticed, within the fraction of a second available to notice, and called it off. Both the vehicle and the pad survived intact and were able to try again. That is the system working. A rocket that launches with 4 engines outside their start envelope is a rocket that has a very bad day somewhere between the tower and stage separation. The abort was the correct outcome, and the fact that it happened at T-0 rather than T-5 minutes is a demonstration of how deep into the sequence the checks run. A second attempt was scheduled for the 20th, then pushed to the 23rd, then to the 24th because Tropical Storm Bertha was in the Gulf. On Friday the 24th at 6:51 p.m. Eastern, it went. The ascent was clean. Stage separation happened as designed. Booster 20 performed its boost-back burn nominally, turning around and heading back toward its target point offshore in the Gulf. And then the landing burn did not go to plan. Only 10 of the Raptor engines relit for the landing burn, and 2 of those shut down within seconds of ignition. Booster 20 hit the water considerably faster than intended and was lost. I want to explain what a landing burn is and why the engine count matters so much, because this is the part of the flight that carries the most information. A super heavy booster returning from the edge of space is falling. It is enormous, it is largely empty, and it is coming down fast. There are no parachutes and no wings. The only thing that can slow it is its own engines firing downward against its fall. And that burn has to be timed and throttled so that the vehicle arrives at the surface with almost exactly zero vertical velocity at almost exactly the right altitude. This is often described as landing on a column of fire, which makes it sound elegant. A better description is that you are balancing a skyscraper on a jet of flame while it falls, and you get one attempt, and the margin for error is measured in fractions of a second. Engine out capability is designed into this. Losing an engine is survivable, but the burn is calculated around a specific amount of thrust arriving at a specific moment. And every engine that fails to light or shuts down early removes a slice of the deceleration budget. 10 lighting instead of the full complement, and then 2 of those 10 quitting almost immediately, leaves the vehicle short of what it needs at precisely the moment it can least afford to be short. So Booster 20 arrived hard, and it did not survive. Here is the important context, though, and it is why this reads as a data point rather than a disaster. Booster 20 was never coming home. There is no landing tower catch on this profile. The target was a soft splashdown at an offshore point in the Gulf, and the vehicle was going to be destroyed either way. The question was only whether it would arrive gently enough to prove the landing burn works. It did not. That is a real failure of a real objective, and it is the second flight in a row with propulsion issues on that phase. SpaceX had explicitly made hardware and software modifications after Flight 12 specifically to address engine out problems, and the modifications did not fully solve it. Now, the upper stage. Ship 40 flew what every technical description of this mission calls a controlled suborbital trajectory, deliberately designed to fall just short of orbit. That word is the one I want to spend time on, because it appears in the engineering documentation for this flight and almost never in the coverage. Suborbital. 13 flights into the Starship program, the vehicle has not been to orbit. I want to be scrupulously fair about why, because this is where a lot of commentary gets lazy and unfair. SpaceX is not failing to reach orbit. It is choosing not to. The performance to get there exists. What SpaceX is doing is flying a trajectory that reaches orbital altitude and very nearly orbital velocity, but deliberately falls a fraction short. So that if the vehicle loses control or the engines cannot be relit, it comes down in a predictable patch of ocean, rather than staying up and re-entering somewhere nobody chose. It is a safety decision, and it is a sensible one. A fully orbital Starship that goes silent is an uncontrolled multi-hundred-ton object with an unpredictable re-entry footprint. But the reason it matters for Mars is this. Everything that comes after Starship works only in orbit. Propellant transfer happens in orbit. Long-duration coast happens in orbit. Departure for another planet happens from orbit. Every capability on the critical path to Mars begins after the point Starship has not yet crossed. That does not make the program a failure. It does tell you precisely where it currently sits on the road, and it is earlier on that road than the public conversation generally assumes. So what did Ship 40 accomplish? It deployed 20 Starlink version 3 satellites. This was the first time a Starship has released operational hardware rather than simulated mass. And it worked. The satellites extended their solar arrays and antennas and made contact with ground receivers, including attempts to link with stations in South Africa and with the wider Starlink constellation using high-capacity laser terminals. Because of the suborbital trajectory, these were deployed on a path that would not keep them up indefinitely. This was a deployment mechanism test with real satellites, not a constellation delivery. Still, the payload door, the dispenser, the separation sequence, and the satellite commissioning all functioned, and that is a genuine milestone. Starship went from a test article to a vehicle that has released working spacecraft. After deployment, Ship 40 coasted for roughly 27 minutes. Then, relit a single Raptor engine as a maneuvering test. Relighting an engine in vacuum after a long cold coast is another item on the Mars prerequisite list, because a Mars departure burn is exactly that, an engine lighting in space long after launch on a vehicle that has been sitting cold. Then it came home. Ship 40 pushed through the phase of maximum dynamic pressure and the region of peak heating and splashed down in the Indian Ocean west of Australia, where a SpaceX recovery team had deployed camera carrying buoys to try to capture the arrival. That is the flight. A hard-won launch, a clean ascent, a first payload deployment, a successful in-space relight, a survived reentry, and a lost booster. Now let me come back to the cameras, because this is the part that reframes everything. 6 of those 20 satellites carried camera suites for one purpose: to photograph Starship's heat shield and downlink the imagery so operators could assess it. SpaceX has stated the goal directly, which is to develop methods of analyzing heat shield readiness for return to launch site on future missions. Think about what that means. Before SpaceX can bring a Starship back to the pad and catch it, it needs to know, from orbit, whether the thermal protection system is intact enough to survive the trip down. You cannot send an inspector. You cannot walk around it. So you take photographs from outside using something already going along for the ride. And SpaceX considered that important enough to spend 6 of its first 20 operational satellites on it. Which brings us to the single largest technical obstacle between Starship and Mars. And it is not the engines, and it is not the software. It is the heat shield. Here is the physics. A vehicle returning from low Earth orbit hits the atmosphere at roughly 7.5 kilometers per second. All of that kinetic energy has to be converted into heat and shed, and the heat shield is what stands between the vehicle and that energy. A vehicle arriving at Mars from an interplanetary transfer arrives at a similar or higher velocity, but into a completely different atmosphere. Mars entry generates temperatures exceeding 4,500 degrees Celsius, which is roughly double what Starship experiences returning from Earth orbit. The Martian atmosphere is thin, which means the vehicle stays fast for longer and does its decelerating lower down, and it is predominantly carbon dioxide, which behaves differently and more aggressively against thermal protection materials than the nitrogen and oxygen mixture the shield was designed around. And here is the sentence that should stop anyone confident about near-term Mars. As Musk himself has pointed out, nobody has ever developed a truly reusable orbital heat shield. Not SpaceX, not NASA, not anyone. The space shuttle came closest, and its tiles required extensive inspection and replacement after every single flight, which is a large part of why the shuttle never achieved the turnaround times it was sold on. Then there is the landing problem. The Starship upper stage is roughly 52 meters tall and weighs over 200 tons. Every spacecraft that has ever successfully landed on Mars has been a fraction of that. Curiosity, at around 900 kilograms, required a sky crane. Starship is on the order of 200 times heavier than anything that has ever touched down there, and it has to do it with rocket engines, in an atmosphere too thin to help much and too thick to ignore, on terrain nobody has surveyed at landing precision. SpaceX's preferred site is Arcadia Planitia, chosen because it is broad and flat, has abundant shallow water ice for eventual propellant production, and sits at low elevation, which means marginally more atmosphere above it to decelerate through. Every one of those criteria is an admission of how tight the margins are. But the heat shield is not the thing that stops you departing. That honor belongs to orbital refueling. And the numbers here are the ones that settle the timeline argument. Starship uses essentially all of its propellant just reaching low Earth orbit. It arrives with a full payload bay and empty tanks. To go anywhere beyond Earth orbit with meaningful cargo, it has to be refilled up there. The way that works is that additional Starships, configured as tankers, launch, rendezvous, dock. and transfer liquid methane and liquid oxygen into the Mars-bound vehicle. Each Mars-bound Starship requires roughly 1,200 tons of propellant. Published estimates put that at somewhere between 8 and 15 tanker flights per vehicle. The planned SpaceX had been working toward called for 5 uncrewed Starships in the 2026 window. 5 vehicles at 8 to 15 tankers each is somewhere between 40 and 60 launches inside the window, which is a matter of weeks. No rocket program in history has achieved that cadence. SpaceX's own Falcon 9 fleet, the most prolific launch system ever operated, achieves a launch every few days across multiple pads with a vehicle that has flown hundreds of times. Starship has flown 13 times in total. The cadence problem is what several independent engineers have focused on. Stephen Berg, an assistant professor of aerospace engineering at Rutgers, has been among the more vocal skeptics, and his objection is precisely this: not whether refueling is physically possible, but whether the turnaround can be compressed to days rather than weeks. Phil Smith, a space industry analyst at Bryce Tech, has described orbital refueling as significant but not insurmountable, which is roughly where the informed consensus sits. It is an engineering problem, not a physics problem. Engineering problems still take years. And the demonstration has not happened. The closest SpaceX has come was a 2024 test in which roughly 5 tons of liquid oxygen were transferred between 2 internal tanks inside a single vehicle. That is a meaningful proof of concept for fluid behavior in microgravity, and it should not be dismissed. But it is not the same operation. Moving propellant between 2 tanks in one ship does not require rendezvous, docking, a cryogenic mating interface, or the management of 2 separate vehicles' attitude and thermal states. Transferring large quantities of cryogenic propellant between 2 separate spacecraft in orbit has never been done by anyone, and it remained undemonstrated as of this flight. There's also a problem that gets almost no public attention, and that engineers worry about a great deal. Liquid oxygen and liquid methane are cryogenic, meaning they are stored at temperatures far below anything in ordinary experience. When you pump them into lines and tanks that are relatively warm and empty, some of the propellant flashes straight to gas on contact. These are called parasitic losses, and they are not trivial. If you lose too much on every transfer, you need more tanker flights per Mars vehicle, and the launch count that was already unprecedented gets worse. SpaceX had planned to demonstrate orbital refueling in 2025. That slipped. Musk indicated it might be achieved by the end of 2026, and then, in his own words, described a 2026 Mars attempt as a low probability shot and somewhat of a distraction. Which brings us to February, and the decision that most people covering Flight 13 have not mentioned. On the 9th of February 2026, Musk announced that SpaceX was delaying its Mars ambitions by 5 to 7 years in order to concentrate on lunar missions. There were 3 reasons, and they are all defensible. The first is that orbital refueling remains unsolved at operational scale, and it is the gate through which everything else must pass. The second is contractual. Starship is the human landing system for NASA's Artemis III mission, the flight intended to return astronauts to the lunar surface. That is a binding commitment worth billions of dollars, and Artemis III has already slipped to no earlier than 2027 or 2028. With Starship development identified as a principal reason, NASA's Office of Inspector General warned in a March 2026 report that Starship delays were threatening that timeline. When you owe a government agency a moon lander, the moon lander comes first. The third is that SpaceX's other demands on Starship have expanded considerably, including Starlink version 3 deployment, which is precisely what Flight 13 was testing. So the 2026 Mars window has effectively passed as a realistic target. It did not pass because of anything that happened on Friday. It passed in February, publicly, and Flight 13 is simply the flight that makes it visible. Now, the window arithmetic, because this is what determines what happens next, and it is the least understood part of the whole subject. You cannot leave for Mars whenever you like. Earth and Mars orbit the Sun at different speeds, and the efficient transfer path is a long curved arc that has to be launched at a moment when Mars will arrive at the meeting point at the same time as the spacecraft. That alignment recurs roughly every 26 months. Miss it, and you do not lose a week. You lose about 2 years. The 2026 window opens in the closing months of this year. The one after that falls in late 2028, running into early 2029. So the meaningful question is not whether Flight 13 killed the 2026 window. It is what Flight 13 tells us about 2028. Between now and then, in roughly 28 months, this program needs to demonstrate full orbital flight, ship-to-ship cryogenic propellant transfer at scale, tanker turnaround measured in days, a heat shield validated for reuse without teardown, booster recovery that works reliably rather than intermittently, and a landing system capable of putting 200 tons down on Mars. And it needs to do all of that while delivering a moon lander for NASA under contract. Flight 13 in July 2026 was a suborbital test that deployed satellites successfully, relit an engine successfully, re-entered successfully, and lost its booster on the landing burn. Draw your own conclusion about 2028. Mine is that Musk's revised 5 to 7 year figure, which points at the early 2030s, is the first Mars timeline from this program that looks like it was estimated rather than aspired to. Now let me be honest about what this does not mean, because the cynical read is as wrong as the breathless one. Flight 13 was not a failure. It achieved most of its primary objectives. First operational payload deployment, successful satellite commissioning, successful in-space relight, successful reentry through peak heating, successful splashdown. Judged against what SpaceX set out to do, it was a good flight with one significant miss. The booster loss is not evidence the vehicle does not work. Boosters on this profile are expended. The failure was of a test objective, not of a mission. The pace is not slow by historical standards. 13 flights of a fully reusable super heavy lift vehicle in about 3.5 years, iterating hardware between flights, is extraordinarily fast compared to how launch vehicles have historically been developed. The Saturn V flew 13 times in total across the entire Apollo program. Comparing Starship's pace to Musk's own predictions makes it look slow. Comparing it to how rockets actually get built makes it look remarkable. And the abort on the 16th is not a sign of a troubled rocket. It is a sign of a rocket with a functioning nervous system. 2 more things worth addressing directly, because they circulate constantly. Starship is not a scam or a permanent money pit. It is deploying operational Starlink satellites now, and Starlink generates substantial revenue. The lunar variant is under NASA contract. This is a vehicle with paying work. And the Mars goal has not been canceled. It has been rescheduled, publicly, with stated reasons, by the person whose timelines were previously the optimistic ones. That is different from abandonment, and treating a delay as a betrayal is how people end up unable to distinguish between a program in trouble and a program being managed. So where does the honest assessment land? Between 2 errors, as usual. The first error is the fan reading. Flight 13 succeeded, therefore Mars is on track. It is not. Nothing on Friday demonstrated any of the capabilities that Mars actually requires. The flight was suborbital by design, no propellant was transferred between vehicles, and the booster was lost on the one recovery objective it had. The second error is the cynical reading. The booster crashed, therefore the program is failing. It is not. This vehicle deployed real satellites on a real mission for the first time, survived re-entry, and relit an engine in vacuum after a long coast. Those are hard things, and they worked. The accurate reading is narrower and more useful than either. Starship is making steady progress on the problems it is currently working on. And the problems it is currently working on are upstream of the problems Mars requires. The program is not stalled. It is earlier in the sequence than the marketing implies, and the February decision to prioritize the moon is the clearest evidence that SpaceX's own leadership now agrees. Here is what would change the assessment, and these are the specific things I'll be watching. The first is a fully orbital flight, not a controlled suborbital trajectory that falls deliberately short, but insertion into a stable orbit followed by a deorbit burn. That single flight would unlock everything downstream, and until it happens, nothing downstream can be tested. The second is the ship-to-ship propellant transfer demonstration. 2 starships, docked, moving cryogenic propellant between them. This is the master switch. Watch specifically for reported figures on how much propellant was transferred versus how much was lost to boil off, because the loss fraction determines the tanker count, and the tanker count determines whether the cadence is achievable. The third is booster recovery reliability. Not one successful catch, but consecutive successful landing burns with full engine ignition. Flight 12 and Flight 13 both had propulsion issues on that phase, and SpaceX modified hardware and software between them specifically to fix it. If Flight 14's landing burn is clean, that is a real signal. If it is not, that is a pattern. The fourth is turnaround time. Watch the gap between flights, and more importantly, the gap between a specific booster flying and that same booster flying again. Mars needs days. The program is currently working in months. The fifth is heat shield data. Those 6 camera satellites exist to produce it. Watch for any statement about tile condition after reentry, and particularly for the first flight where SpaceX attempts a return to launch site rather than an ocean splashdown, because they will not attempt that until the imagery tells them the shield holds. The sixth is Artemis. Because Starship is contractually the lunar lander, the Artemis III schedule is now the best available public proxy for Starship's real maturity. If Artemis III slips again, Mars slips with it, whether or not anyone says so. I want to end on the detail that has stayed with me, because I think it captures this whole moment better than any timeline. On Friday, a rocket taller than a 30-story building lifted off from a beach in Texas, threw 20 satellites into space, and those satellites woke up, unfolded their solar panels, extended their antennas, and started talking to ground stations on another continent using lasers. And 6 of them turned around and took photographs of the underside of the rocket that had brought them, so that engineers on the ground could look at some ceramic tiles and try to work out whether they were in good enough condition to risk bringing the next one home. That is where this program actually is, not departing for another planet, checking whether the tiles held. It is not the story anybody sells. It is the story the flight told, and it is the one that will decide what happens in 2028. The next window opens in about 4 months, and nothing is going through it. We'll be watching Flight 14,